In this video, we're going to start chapter 6. And chapter 6 is titled Understanding Organic Reactions. And it's actually kind of an odd chapter. What we're really doing in this chapter is we're laying the groundwork for the rest of the text. So the rest of the chapters this semester and then also in 236 are going to be using some of the concepts that we're going to introduce in this chapter. So really just kind of preparing us for what's coming next is what this chapter is about. We're going to look at some common notation for writing organic reactions. We tend to write them a little differently than you would have seen in general chemistry. We're going to look at common types of organic reactions, start talking a little more specifically about mechanisms. You're going to be spending a lot of time doing mechanisms from here on out. And then talk about energy changes and a little bit of kinetics. So again, just really prepping us for what's to come. So the first part is writing organic reactions. So essentially some common notation. So we're still writing reactants, right, on our left. We still have an arrow. We're still writing our products on the right. So that part's still standard. However, sometimes we write one of the reactants on the arrow. Sometimes we'll write it below the arrow. Sometimes we'll write it on the reactant side of the arrow. I don't always write all the products. Often I will only write the organic product, so it'll look like our reaction isn't following the law of mass conservation. We have to, we're just not necessarily balancing it anymore. So it looks a little weird coming out of general chemistry where you have to account for every little atom and there's a very strict way that you have to do it. It's a little bit different in organic. We do have a term that you may have heard before, but maybe not, and that's a reagent. Sometimes I'll use this term, sometimes I'll still use the word reactant, we'll use both, but the reagent is the substance that the organic compound is reacting with. It could actually be organic itself, but it's not the focus of my reaction. It's what I'm adding to my reactant to make it react. So the substance that the organic reactant reacts with. So it is still a reactant, but because it's not the focus of my reaction, it's just what I'm adding to it, we tend to call it a reagent. Sometimes it's written on the reactant side of the arrow, sometimes it's actually written on the arrow. So an example, if I was to take this alkene and then I could add bromine to it, bromine is my reagent in this problem, right? My alkene is my organic reactant. Bromine is what I'm adding to that organic reactant. So bromine would be my reagent. Oftentimes it's written on the arrow. I tend to write it on the arrow more than I do to the left of the arrow. So that's kind of more commonly how I'm going to write it, though I do both, but they mean the same thing. In both cases, my bromine is my reagent. And again, both of these are equally correct. One is not better than the other. So they're the same, right? Sometimes I'm writing it on the reactant side, sometimes I'm writing it on the arrow. Other things that you'll see, sometimes solvents are included. Sometimes we actually need light energy, so sometimes light energy will be included. Our abbreviation for light energy is often HNu, which might look kind of weird, but if you remember back from general chemistry, you had an equation for calculating energy, and it was Planck's constant, which is H, multiplied by nu, which is my frequency. So H times nu is light energy, so often we'll write it as H nu. There is other notation, but that's the one that I tend to use. So sometimes light energy is included. Sometimes we need heat. That can be written a few ways. We could actually write the word heat Sometimes you'll have a capital delta. Sometimes you'll actually see a temperature. So if we were to write 80 degrees Celsius, we are heating it up. 25 degrees Celsius is considered room temperature, so 80 is heat. So delta symbol, the word heat, and actual temperature, I tend to use all of those. An example, so I have an alkane. I'm adding bromine to it, so this is my reagent again. And then carbon tetrachloride is my solvent, and then we'll add some light energy, so H nu. Here I'm writing my solvent on the bottom. It doesn't have to be. It could be on the bottom, it could be on the top. I could put them all on the bottom, I could put them all on the top. I could put my reagent on the left side of that arrow. So if I was to write Br2, my carbon tetrachloride, right? HCl4 is carbon tetrachloride. And then my light energy, those are equally correct. They mean the same thing. It becomes habit for folks that are first learning or for students to think if it's on the bottom, it has to be the solvent. If it's on the top, it's my reactant. That's not always true. I tend to write it that way, but it doesn't have to be that way, so be careful. My solvent could be on top of the arrow or below the arrow. And same with light energy and heat. The solvents, let's say, etc., could be above or below the arrow. Sometimes we'll see a catalyst. Let's add that to our list. Other things that you'll see sometimes is that if you actually need two reactions, so two sequential reactions, each with a different reagent, we will show that by putting a number 1 and 2 next to the reagents. So if two reactions, and if it's 3, we could have 3 sequential reactions, we would put 1, 2, and 3 next to the reagents. So if 2 sequential reactions are needed, a number is given with each reagent. An example for this one. So I have this ketone, and then we're going to add CH3 magnesium and then a Br. This is a Grignard reagent. You'll learn this reaction actually in 236. And then in a second step, I'm actually going to add a strong acid. So when we have notation like this, what we're saying is we're going to take the ketone, we're going to first react it with my Grignard reagent, then we're going to add the acid. What would happen usually if you put all of them together in the same reaction vessel is that the acid would probably react with the Grignard reagent. So like my 2 reagents would just react with each other. So what we need to do is do the first step first, and that's why the number 1 is there, and then the second step. It's not uncommon to have a third step also. You would just then have a 3. I guess it's probably worth mentioning too, my product from this is actually going to be this. It's a acyl addition reaction. But we also get this as another product. And oftentimes I'm not even going to show that. I'm going to focus on just the organic portion, not the inorganic portion that I get. So we're not even really balancing it, right? If I was to write this, I probably wouldn't even include this. And from like a law of mass conservation and everything that you learned in inorganic, like this is just not right? Like where did magnesium go? Where did bromine go? Like they can't just disappear. They didn't. They're there. We're just not writing it. So this doesn't necessarily need to be included. Sometimes it is and sometimes it isn't. It's not like we're not obeying the law of mass conservation. We haven't created some new sort of way that things react. We're just not showing all of it. So that can be frustrating for folks also when you're first learning organic reactions. You've had it kind of drilled into your head for so long that you need to account for every atom on both sides of the equation, and we're not really doing that. I do want to go through some of the common types of organic reactions that you're going to see. And there are others. These are just the ones that are more common, thus the term common types of organic reactions. And our first one is substitution. And in chapter 7, we're going to do substitution reactions. So substitution. We're going to do substitution reactions in other chapters also, but chapter 7 is entirely on substitution reactions. And they really are just as how they sound. We're going to substitute one group on our organic molecule for another group. We're essentially going to break a sigma bond and we're going to form a new sigma bond. So an example, I have this alkyl halide, and then I'm going to add cyanide ions to it. Probably would have a corresponding cation, right? Sodium would probably be here. I'm just not showing the sodium. If you remember your solubility rules from chemistry past, it would be Na plus and Cn minus, and my sodium would actually be a spectator ion, so I'm just not including it. Sometimes I will include it though, just a heads up. And what I'm going to end up doing is substituting that bromine with that cyanide. It is attached to the carbon there, not the nitrogen. And then my other products, if you wanted them, I have Br minus, and then it's hanging out with the sodium ion, right? But my sodium would be a spectator ion. If you remember writing your ionic equations from chemistry past, they would just get canceled. So substitution, we're literally substituting. I'm just making this look nicer here. So I had a bromine bonded to my carbon. I now have a cyanide group bonded to my carbon, and then bromine's by itself. Actually not by itself, right? It's hanging out with sodium, but I didn't include it. We can do another example. That first one I did is what the type of reaction we'll see in chapter 7. This one here is one that you'll see in 236. So I have another ion. It would probably have a cation with it, right? We can't go into lab and just get a jar of anions off the shelf. So it would have, probably a potassium or a sodium ion with it, maybe lithium. But we're going to end up substituting that chlorine for that methoxy group. The name of that group is methoxy. It's a methoxide ion when it's by itself. Don't worry about the name yet. We'll learn to name them later. But I just wanted to give another example of a substitution. And then, of course, chlorine's floating around, but often I don't draw those. And you don't have to put the plus sign either. If you guys are wondering about the plus sign, that doesn't have to be there neither. You can just draw all of your products on the product side and it's fine. So for us, chapter 7, we will see them in other chapters, but chapter 7, its focus is actually going to be substitution reactions of alkyl halides, which is what my first example here was. My second type of common reaction is going to be an elimination, which is also how it sounds. We're going to eliminate something from my organic molecule. And chapter 8 is going to be focused on elimination reactions of alkyl halides. So I'm gonna draw a generic version first. So I'm putting an X and a Y on here. X doesn't have to be a halogen. I'm just using two different things. And we're going to end up eliminating both of those and forming a pi bond between them. So then I would have, they don't necessarily have to be bonded to each other, but they would be eliminated. So they would also be a product. So what we're doing with this one is we're forming a pi bond. I said this up on this one, but I didn't write it down. We should say that. We're breaking a sigma bond and then forming a new sigma bond. So a sigma bond is broken, but a new sigma bond is formed. So we broke the sigma bond between carbon and bromine. We formed the sigma bond between carbon and the carbon of that cyanide group. If I go down to my elimination, we're forming a pi bond. An example for us. So we'll use an alkyl halide again. And I'm going to add sodium hydroxide. We'll show the cation this time. So again, it is sodium with a positive charge and then my hydroxide ion with a negative charge. It's the hydroxide ion that's actually going to do the reaction. And we will learn this mechanism in chapter 8. But what I'm going to end up with is my alkene. And then my other products, if we wanted them, I'm actually going to have water. And I can show you that. And then sodium is hanging out probably with bromine, right? Sodium has a positive charge and bromine has a negative charge. So if we go up and we look at my little generic example, right? I removed 2 things. And this one, I did also remove 2 things. It just doesn't necessarily look like it, right? There's 2 hydrogens. You can color code them on this carbon, right? It's sp3 hybridized. And then over here, because it's now sp2 hybridized, right? We form that pi bond, it only has 1 hydrogen on it. So we actually lost a hydrogen, we actually lost a hydrogen in that bromine. So if we wanted to color code, I could make one of those hydrogens pink because I'm showing the pink one being lost. And actually, let's keep that bond black because those electrons are coming from the oxygen, not from the hydrogen. So we are losing things across, right, from adjacent carbons, and then that double bond is being formed between them. When we're drawing skeletal structures, we don't have to show those hydrogens, so it's not always really obvious that we lost a hydrogen until you look at the hybridization, right? We're going from an sp3 hybridized carbon to an sp2 hybridized carbon, right? We're forming that pi bond. So I'm going from 4 electron groups on it to 3 electron groups. Still 8 electrons, but I have those extra pi electrons on that carbon after it reacts. Our next type is an addition reaction, and honestly, addition reactions are really just the opposite of our elimination reaction. If I was to take my arrow from my last example and turn it around, addition. So addition, so for these ones, we're actually breaking a pi bond, right? If it's the opposite of an elimination, we're forming a pi bond. Here we're breaking a pi bond. So an example, I'm going to start out with an alkene, and let's add HBr. And I'm going to end up putting a bromine on one side of that double bond, a hydrogen on the other side of that double bond. And I'm going to end up with this, right? Because I'm showing skeletal structures, I don't have to show those hydrogens, but I did have 1 there. I now have 2 here, right? One of those hydrogen is coming from here. The other hydrogen was the original. So I am adding across that double bond. If we were to do I should have done this one first, our little generic version, right? I'm taking my reagent and I'm adding it across that double bond. So I'm breaking my pi bond. So a pi bond is broken. And we're going to see these in both chapters 10 and 11. Chapter 9, which I haven't written down, right? I have chapter 7 for substitution, chapter 8 for elimination. Chapter 9 is going to have both elimination and substitution in it. So we get to do that in those chapters also. And then addition reactions we'll see in 10 and 11 mostly. And then our last one, you're actually not going to see this semester, but you will see it in 236, and that's a rearrangement. And what we're doing with the rearrangement reaction is we're actually producing an isomeric product. So our product is an isomer of our reactant. Producing is what that was supposed to say. Produces an isomeric. And actually, as I'm writing this, we do see one example of this semester. So as part of one of our addition reactions, we actually have a rearrangement that occurs as part of it. So we do an addition and then a rearrangement. So you will get a chance to see one type. I don't always do the mechanism for it. It just depends on time. But we do have a rearrangement. And this is actually the particular one. So I have this. So I have an alkene and an alcohol in the same carbon. So we actually call this an enol. So when we name molecules, our alkenes are going to end in ene, right? Our alkanes ended in ane. Our alkenes are going to end in ene. And then alcohols end in -ol. So because I have on the same carbon an alkene and an alcohol, we can call it an enol. So this carbon has both. Be really careful. You can have them on the same molecule, but it's not always called an enol because they're not on the same carbon, right? This has an alkene and an alcohol. And when I name it, I'm going to use both of those prefixes. But if you just say it's an enol, it typically means they're on the same carbon. And you don't need, I'm not going to test you on that name right now. It's just I'm going to probably say it in the course of this explanation, and I want you to know what we're doing. So I'm going to add a strong acid to it, and it's going to react with my enol, and we're going to produce a ketone. And if we were to figure out our molecular formula, right, in my enol, I have 1, 2, 3, 4 carbons. I have 1 oxygen, and then I have 1, 2, 3, 4, 5, 6, 7, 8 hydrogen. And then if I look at my ketone, I still have 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8. So 8 hydrogen, and then 1 oxygen. So those would be constitutional, right, or structural isomers of each other. So we didn't substitute, we didn't eliminate, we didn't add, we rearranged. So a rearrangement reaction. So just going back up and reviewing these real quick. So substitution is kind of nice. The name tells us what we're doing. We're literally substituting. So we're replacing one group with another group. We're breaking a sigma bond and then making a new sigma bond because we're replacing it, right? We're not just getting rid of it. Elimination, we're removing things from adjacent carbons, and then a pi bond is going to form between those adjacent carbons. So the things that you eliminate have to be from adjacent carbons. It might be worth adding that. So eliminates, right? Remember that double bond is going to go between 2 carbons. So the things that I remove have to be on those 2 carbons that the double bond is going between. So we eliminate from adjacent, right? Carbons that are next to each other. And then our addition is the reverse of that, right? We're actually breaking our pi bond. We're adding things across that double bond, right? It's an addition reaction, and we're adding them to adjacent carbons. We're adding them to the carbons that have that double bond. The double bond's not going to go away, or I don't have a way to add. Like I can't go, if I was to add more carbons here, I can't go and add something to that carbon because it already has, right? It already has an octet. There's 2 hydrogen on there. Unless I was to break a hydrogen and then add something, which would make it a substitution, not an addition. So addition, we're breaking that pi bond. We're adding things to adjacent carbons. We're adding it across the double bond is kind of how you would say it. So we add across the double bond. And then rearrangement is literally just that. We're rearranging. So we're getting an isomer, a constitutional isomer of what we started out with.